do a good job. Okay, but my expectation then from you guys is you got to really be with me on this. Okay, so I want to look at we're going to skip through the next unit. We're going to cover 2 sections in chapter 5 and then chapter 6. We'll skip most of chapter 5. A lot of it is just really not that big a deal. 5.5 is important. There's a couple things in 5.5 that you need to know about. Okay, and here's the stuff that I want you to be. AJ, quiet, please. Okay, here's the stuff I want you to by the end of today. I want you to have an idea how to think about some of this stuff. Now it's going to take some practice to get it all down, but I want you to be familiar with these concepts. I want you to be able to use the triangle measurements, so angles and sides, to determine which is the longest side and which angle is the largest. So for example, if you know the angle measures of a triangle, I want you to be able to tell me which side is the longest and which side is the shortest, and vice versa. If you know the side lengths, I want you to tell me which angle is the greatest and which is the least. And then also I want to introduce you to the triangle inequalities. And that's really it. Okay, so what's this all about? Well, I mentioned this earlier in the week, but it officially comes up in the book in section 5.5. We know that the largest angles in a triangle are always opposite the longest sides. And the smallest angles in a triangle are always opposite the shortest sides. A way of thinking about it is the biggest angles always look at the biggest sides across the triangle, and the smallest angles always look across the triangle at the shortest sides. Okay? So, for example, if we are given something like this here, where we have triangle ABC, and we know that side AB has length 3 and side BC has length 5, that's not enough information for me to determine what the size of those angles are. But I can tell you for sure that the angle opposite the side with length 5 is greater than the angle opposite the side of length 3. So the measure of angle A is definitely greater than the measure of angle C, even though I don't know what they are. I know that relationship. Okay, can anybody tell me here what is the, and you can't see it yet, it'll go away in a second, but that's DEF. That's an E over there in the corner. Pretty soon, go away. There we go. Okay. So, don't say it out loud yet, but I want you to look at this and see if you can determine on your own here what is the largest, what's the longest side in that triangle, and what is the shortest side in that triangle. Don't say anything. What's the longest side and what's the shortest side in that triangle? What do you think? Do you have any ideas? Volunteer? Yes, sir. Eric. DE is the longest side. Good. What's the shortest side? Somebody else? Yes, ma'am. Yeah, good. How'd you get that? How'd you get the longest side? Eric, what'd you do to get that? What goes there? You must have figured out what goes there. Okay, yeah, it's going to be 80, right? Well, and you can't just tell, because if you look at the triangles, I purposely have drawn the triangles so they are not to scale. So they're not going to look right. Don't go by the look of the triangle. You got to go by the measurements in the triangle. So what is the length of the missing angle, or the size of the missing angle? 80. It's 80 degrees, isn't it? Okay, good. So if that's 80 degrees, that's the biggest angle. So it has to be looking across the triangle at the longest side. So the longest side is DE. Good. The smallest angle is obviously 40. So 40 has to be looking across the triangle at the shortest side. Okay, make sense? No big deal. Could you tell me here, real quick, what's the, just as a class, what's the longest side? HG, good. What's the shortest side? HJ, makes sense? Okay. What is the largest angle?
P.
Angle P, because it's opposite the biggest side. Good. What's the smallest angle? R. Good. Okay, you got it. Okay, something else that comes up in 5.5. This is really minor thing. This makes total sense. Now, if you know, and a lot of you guys had forgotten, I got a lot of questions about this as of, through Wednesday, but I think it's starting to, people are starting to kind of get the hang of this a little bit. It's been a while since we talked about it. People have forgotten the exterior angle theorem. The exterior angle theorem, remember, is the one that says if we extend one side of a triangle to create an exterior angle, like angle 1, then the measure of that exterior angle is always equal to, if I look at the 3 interior angles in the triangle, it's the sum of the 2 that are far away, that are not next to the exterior angle. So not angle C, but angle A plus angle B, the measure of angle A plus the measure of angle B, equals the measure of angle 1. That's the exterior angle theorem. So let's write that down to remind ourselves. So we know that's true. Measure of angle 1 equals the measure of angle A plus the measure of angle B. So could you tell me then, if the measure of angle 1 equals the measure of angle A plus the measure of angle B, how does the measure of angle 1 compare to the measure of angle A by itself or the measure of angle B by itself? Is it, and all I'm asking, is it going to be greater than or equal to or less than? It's got to be greater than, doesn't it? Because if the measure of 1 equals A plus B, then A by itself must be smaller, right? And B by itself must be smaller. That's the exterior angle inequality. That's all it is. The measure of an exterior angle is always greater than each of the remote interior angles by themselves. Okay? No big deal there. So far, pretty minor stuff. Okay, where we get into something a little different is with the triangle inequality. This one, conceptually it's pretty simple, but you can get some questions where the algebra gets a little trickier. So I want to look at an example. What this tells us is not every group of 3 segments could be turned into a triangle. Some of them don't fit properly. So for example, if I take these, group A, group B, and group C, each of those groups has 3 segment lengths. Only one of those groups actually produces a triangle. Which one? A. Not A. A doesn't work. Let's take a look. See what happens with these if we draw pictures. Here's the problem with A. If I try to make a triangle out of group A, I've got, 2 sides that have lengths of 2 and one side that has length of 5. Now, when I put those short sides together and I hinge them at the corners and I try to pivot them down so that they'll meet and form a triangle, they never meet. How come? Yeah, because they only equal 4 together, right? And they need to equal more than 5, right, in order for this thing to make a triangle. What about group B? Now with group B, the 2 short sides add up to exactly the length of the long side. That's a problem also, because when I swing them down to try to meet, so that they'll point C and point D will meet to form a triangle, where do they meet? Yeah, when it goes totally flat, right? And that's not a triangle. The only one that actually works is the third group, because in the third group, the 2 shorter sides of length 4 and 2 add up to a greater length than the third side, which is 5. And so when we swing them down, they actually meet and form a triangle. Okay, so what this amounts to then is a relationship called the triangle inequality. And it just says that the sum of the lengths of any 2 sides of a triangle has to be greater than the length of the third side. So it's kind of awkward to call these AB and BC and AC. Let's do something a little different. How about if we let's just call this side 1, let's call that side 2, and that side 3, right? So then what has to happen is the length of 1 plus the length of 2 has to be greater than 3. That's one thing that has to be true. That's kind of awkward too, because those look like, I don't want to do it that way either. Hang on. Let's call them something different. Let's call this side A, let's call this side B, and let's call this side C, and let's ignore these guys. Right? Make sense? So A plus B has to be greater than C, right? Has to be true. But also, B plus C has to be greater than A, and A plus C has to be greater than B. All three of those things have to be true by the triangle inequality. All right? So what that amounts to then, or where that's useful, is when we're trying to solve a problem like this. Okay, so what about this then? If we know that we have a triangle that has two sides of length 10 and 14, but we don't know what the third side is, the question is, describe the possible lengths of the third side. Now in algebra, what do we do when we're trying to find the value of something that's unknown to us? What do we typically do? Yeah, we call it a variable, usually x, right? So we'll let the length of the third side, we'll just call that x. Okay, so we know that the three sides in the triangle have lengths x, 10, and 14, right? Okay, now by the triangle inequality, we know that the sum of any two lengths has to always be greater than the third. Now let's look at the extreme cases. Let's look at the cases, the important cases, the cases where x is the shortest side, because that's going to give us the shortest possible value of x, the smallest value. And let's look at the case where x is the longest side in the triangle. And that'll give us the limit, the upper end of it, the longest that x could be. If x were the shortest side in the triangle, what would the longest side be? 14, right? Everybody see that? So if x is shortest, then 14 is the longest, right? So, what does the triangle inequality say? What plus what is greater than what? True, but the length of the two shorter sides has to be greater than the longest side. So if we said 14 is the longest, right, if x is the shortest, then wouldn't that be something like this? X plus 10 has to be greater than 14. Everybody get that? So that's what we get if we assume that x is the shortest side of the triangle. And we can solve that. We can solve that. All I have to do is subtract 10 from both sides, and I get the result x is greater than 4, right? Now, what's going to be, let me pick a different color here. What's going to be the case if x is the longest side? Then what's the triangle inequality that has to be true? Okay, good. The two shorter sides have to add to more than the one long side, right? So then we'd say 10 plus 14 is greater than x, right? And so we get the answer 24 is greater than x. So that gives it to me, doesn't it? That tells me the range of possible sides that x could be. X has to be greater than 4, but less than 24, right? So we could combine that into a single compound inequality if we want to, and just say it this way: x is greater than 4 and less than 24, and that's our answer. Any values of x in between 4 and 24 would work. Okay? Now watch what happens if we choose the other inequality, the one that doesn't really make sense. What if we assume x is the medium side, right? Well, then I would still do this one, wouldn't I? I'd still do this one. Well, what if I use the inequality? See if you can tell me why this doesn't mean much to us. What if I pick the inequality x plus 14 is greater than 10? I don't have much room to write that one, but I'll do it over here. So, 2. AJ, huh? Cool. Okay, so if I take the other one, what if I say x plus 14 is greater than 10. That one's kind of silly. Why would I even do that? Does anybody see something really crazy? I mean, why is that? Yeah, I'm going to get negative, because 14 is already bigger than 10, right? So that's the case I don't even need to consider, but that's the unimportant one. All we need to consider are the cases where x is the shortest or the longest. If I do this one, I'm going to get the answer x is greater than negative 4. Well, that doesn't mean much, right? Okay, so these are the two that matter. Okay. If I look at these, x is greater than negative 4, even if I did do that one by accident, that's okay. I have to pick the values of x that are always going to make all of those inequalities true, right? So would a value like 10 work for all of them? It would, wouldn't it? Because 10 is greater than negative 4, it's greater than 4, and it's less than 24, right? So 10 would work. What about 0? No. Because although 0 is greater than negative 4 and less than 24, it is not greater than 4. So as a general rule, if I've got 3 inequalities like this and I want to make all of them true at the same time, I only keep the two that are the most restrictive, right? Because if I compare these two right here, x is greater than 4 and x is greater than negative 4, all values that are greater than 4 are obviously going to be greater than negative 4, right? So the green inequality takes care of the pink one, right? But values that are greater than negative 4 are not necessarily greater than positive 4. So this one we can just throw out, okay? Because the green one sort of overrides the pink one. Because these green values always make the pink values work, but pink values don't always make the green values work. Does that make sense? But we can, once again, we saw that coming and we would have not even used that inequality in the first place. Okay? Okay, last example. Something like this. Okay, if we want to, this is kind of a hard problem. This is a little bit tricky, so watch this one closely. If I want to solve for x, what am I going to do? Well, I'm just going to come up with the 3 possible inequalities and solve each one, and then I'll look at the answers and pick the range of x's that make all 3 solutions true. So I got to use all 3 permutations of the triangle inequality theorem. So for example, I know that x plus 2, I know that, that's like x, that x plus 2 plus x plus 3 has to be greater than the third side, 3x minus 2, right? That's one thing that has to be true. I also know that x plus 2 plus 3x minus 2 has to be greater than the third side, x plus 3. And I also know that, what's the other combination I didn't do yet? 3x minus 2? Good, plus x plus 3 has to be greater than x plus 2. Okay? Those all 3 have to be true, so I'm just going to solve each one of those. Now, remember back to the very beginning of the year when we worked with inequalities a little bit. We said that doing algebra with inequalities is the same as doing algebra with equations, with one exception. The only difference is if I multiply or divide both sides of an inequality by a negative number, I have to flip the inequality sign. Otherwise, it's the same. So when I'm solving the blue inequality, it's no big deal. I'm just going to do the same stuff I would normally do. X plus x, I'm going to combine like terms, gives me 2x. 2 plus 3 is 5, is greater than 3x minus 2. Now, if I want to solve for x, I'm going to collect the x's on the side where there are most of them to begin with, so I'll collect them on the right, how about? So I'm just going to subtract 2x from both sides, and I'll push the numbers the other way, so I'll add 2 to both sides, right? Just looking familiar? And then I just end up with 3x minus 2x is x, 5 plus 2 is 7. So I get x is less than 7. That's the blue solution, right? What about the red solution? if I combine like terms, x plus 3x is 4x, 2 plus negative 2 just goes away. So I get 4x is greater than x plus 3. Now what? Yep, subtract x, good. And I get 3x is greater than 3. Last step? Good, divide by 3. Divide both sides by 3. So x is greater than 1. That's the red solution. Okay, last one. If I do the green solution, 3x plus x is 4x. Negative 2 plus 3 is plus 1. It's greater than x plus 2. So what do I have to do here? Subtract x from both sides. While I'm at it, what else could I do? Okay, good. Subtract 1. So those go away. And I get 3x is greater than 1. So if I divide both sides by 3, what do I get? Yeah, x is greater than 1/3. So those are my 3 solutions. Now I just have to pick the values of x that are going to make all of those true at the same time. Okay, well, let's see. I know x has to be less than 7, but look at the green and the red ones. X is greater than 1/3, or x is greater than 1. Now, which one of those two, AJ, turn around and face the front, please. Sorry. Which one of those two is going to always make the other one true also? Yeah, x is greater than 1, right? When x is greater than 1, x is obviously also greater than 1/3. But when x is greater than 1/3, it's not necessarily greater than 1. For example, 2/3, right? So I'll throw this guy out, and I'll just keep those two, because those are the ones that always work. So when I combine them, I just get the single answer. X is greater than 1 and less than 7. So those are the values that work between 1 and 7. Those are the values of x that could make that triangle actually work. Okay? I did include, if you're interested in looking at it, I did include a little applet. This is just linked to on the website. If you look under chapter 5, 6 resources, there's just a little applet that you can click on, and it takes you to this. This guy right here. And all this does, look what this is, kind of cool. This demonstrates the triangle, well, it demonstrates the triangle inequality, but it also demonstrates the relationship between sides and angles. Notice that if I drag this thing around, it tells you that the blue side is always the shortest, and the red side is always the longest. But notice that the blue angle is also then going to be the smallest angle, and the red angle is always going to be the biggest angle. No matter how I tweak this triangle, by dragging this point, I always end up with that result.
I got a question.
Yeah.
There would be like two. What happens if they're both the same length?
Okay, if they're both the same length, then it's isosceles, and the base angles will be congruent. Good question. Yeah. What AJ's saying is, what if I made it so these were both, well, let's see if I can do it here, like that. Okay, now it kind of breaks it. Right? If I made both of these 6 point, oh, they're not the same. How come? That was kind of odd. There we go. It's yeah, it's right there. 6.85 and 6.85. So now notice that now still the biggest angle has to be the one opposite the 8.57, which it is. But the other two are just going to be congruent because it's isosceles. But the relationship still holds, right? Yes, sir. Okay, if it's equilateral, good. If it's equilateral, it's also equiangular, right? And so then all the sides are the same length, which would mean, according to our relationship, that all the angles should also be the same length, which they are. Oh, there wouldn't be. They're all the same. You're right. So you couldn't enter it that way. You're right.
Would that be an A answer?
It's something like that. Yeah. I don't know. There'd be instruction. Moodle would tell you, but I won't ask you that one. Okay. Okay. I think we're good.